nth roots, radicals, and rational exponents. So for our next lesson, we are going to go back and review what we learned back in Algebra 1, and it was also taught in our geometry classes on breaking apart a radical and looking at radical form to exponential form and vice versa. And we'll also need to review simplifying radicals, and then we'll get into working out some examples to show you how we can apply that to like real world problems like triangles and things like that. Alright, so let's first review our radical symbol. A lot of times we call it, I made that way too big here. So we don't need that. So a lot of times we call them square root symbols, but they're actually called radicals. Okay, and then we usually have something underneath. Sometimes you'll have a number sitting here on this little ledge, and sometimes you don't. When you do not see a number sitting there, it's an invisible 2. Alright, so let's break this apart. The symbol itself is called a radical. Okay, so again, a lot of times you'll hear teachers and people call them square root symbols, but it's actually called a radical. The little number sitting on the ledge, or when you don't see one, it's an invisible 2. It's called the index. And that tells you how many numbers or variables we want grouped. The number underneath the radical symbol is called the radicand. A lot of fancy vocabulary words here. Okay. Sometimes the radicand can have an exponent underneath. Okay, and we'll get to that as we go. So when I ask you, you know, what groups are we looking for? Are we looking for groups of 2, 3s, 4s? We're going to be looking at the index here. Okay. So also, if you see one without, I'm going to put a little note there. It's an invisible 2. Just like we have an invisible 1 in our denominator of fractions or of whole numbers in fraction form. So if there's not a number there, it's an invisible 2. All right. So next, let's review how we go from radical form to exponential form. Okay. So let's say we have a to the m power, and our index is n. We use n here to say, you know, a variable for any number that could be there. I'm going to go ahead and color code this again. Here's my radical symbol, my index, and my radicand. So if I wanted to convert this back to exponent form, what you do is you take your radicand and it becomes the base. The exponent, and if there's not one, that's an invisible 1, becomes our numerator, and the index is always the denominator. And the more you practice this, you'll get to where you can just write that very quickly. I just usually say, okay, it's a to the m over n power. A to the m over n power. Okay? And just repeat that over and over. So our index is always our denominator. Oh, I colored too much there, didn't I? So I like to use colored pencils. They might not erase perfectly, but they erase a lot better than if I was using a pen. Man, I I'm having a rough time here, aren't I? There we go. A to the m over n power. Alright, well, if I was going to go from exponent form to radical form, okay, so let's say I have a to the m over n power. Sorry, I had to squirt my cat. He's being awful. Okay, so here we go. Our base goes under our radical symbol. I always kind of think that fraction bar turns into a radical. The numerator is my index. Oh my goodness. That is backwards, isn't it? My numerator is my exponent. And my denominator is my index. Okay, so let me show you some examples to try to clear up my mistake I made there. Okay, so up here, let me change colors so they stick out a little bit more for you. Okay, let's say I have an index of 4 and my radicand is a 7 to the 3rd power. So what I do is 7 is my base, 7 to the 3 over 4 power. 7 to the 3 over 4 power. Okay. And let's try vice versa here. I'm going to give one where maybe, let's say I don't have an exponent here. So, well, here. Let's say, okay, I have it 2 to the 3 over 4 power. What would I do? So 2 to the 3 over 4 power. 2 to the 3 over 4 power. Okay. If it was, let's say, 4 to the 1/5 power, it would be 4 to the 1 over 5 power. Usually we don't see the ones, they're invisible. So it would just look like this. It would be 5th root of 4. Okay, let's review simplifying radicals. So the first thing I want to do is I'm going to use a factor tree to factor out 153 by its primes. I'm going to do 3 and 51. 3 times 17. And 3 and 17 are prime. So I'm going to circle those. Okay, and so underneath my radical symbol now, I have 3 times 3 times 17, which is equivalent to 153. Right, if I do not have a number sitting on this little ledge, it is an invisible 2. And this 2 tells me how many groups I am looking for. Okay, so if I have anything repeated twice, that gets to leave the radical. It's like it's ticket out of jail. That if it's repeated twice, like the index, it gets to leave the radical. Which mathematically means 3 times 3 is 9, and the square root of 9 is 3. So 3 gets to leave. 17 is only written once. It is not repeated, so it stays under the radical. So the square root of 153 is 3 square root 17. Alright, so what does that look like when we have variables? Okay, I'm still going to use my factor tree here. For 16, I'm going to do 2 times 8, 2 times 4, 2 times 2. Okay, so the square root of 16 is 2 times 2 times 2 times 2. And you can actually expand this out as well if you're okay drawing out 28 x's. I'm going to do that for you here, but I will also show you how you could do a little bit easier step. So 1, 2, 3, 4. And the more you do this, you'll be able to do a lot of it in your head instead of having to expand it out. If I have 7 groups of 4, which is 28. Okay, my index again is 4, so I'm looking for groups of 4. I have 4 groups of 2, and 1, 2, 3, 4, 5, 6, 7 groups of x's, so you get square root of 16 is 2, and x to the 1, 2, 3, 4, 5, 6, 7 groups. Okay, so that does seem a little bit excessive. I mean, I'm sure you're thinking, okay, there has got to be an easier way than this, Miss H. And you're right. What we could do is say, okay, well, I have 28 x's. I know I need them groups in 4, and I'm going to have 7 whole groups. And then, of course, if you get a remainder, they would just stay underneath the radical symbol. So let me show you now another way how you could reduce this 4th root of 16 to x to the 28th power by using the radical form to exponential form. Might be easier for you. So here we go. Let me try it with exponential form. Okay, so what we would do is, remember, it's going to be some broken down to, still going to break that, 2 to the 4th power, x to the 28th power, 4, and then I'm going to say 2 to the 4th power over 4, x to the 28th power over 4. Anything to the 1st power is itself, and 28 divided by 4 is 7. And we're going to practice with this, both versions, and you can see which one you feel most comfortable with. This one really will help it when we see negatives. But let me work out a few more examples just to keep practicing here. Okay, so let's try this one. Let's say 4th root of 16x to the 12th power. Again, you can use your factor pairs and factor this apart. It'd be 2 times 8, 2 times 4, 2 times 2. Circling all our primes using that prime factorization. Okay, and for your x's, we can expand those out, 12 of those. And look at your index. Your index is 4, meaning we want to split them in groups of 4. So I see 2 gets to leave the radical, and x to the 3rd power gets to leave the radical. So we get 2x to the 3rd power. Or if you wanted to use exponential form, we would say it is 2 to the 4th power, x to the 12th power, so it would be 2 to the 4 over 4 power, x to the 12 over 4 power. Anything to the 1st power is itself, and x to the 3rd power. I'm going to be honest, I'm more partial to this method over here just because I've used it a lot more in Algebra 1. But I do want to show you some more examples of our exponential form just so you can get comfortable with it. When we start to see negatives, it makes it a lot easier, I think. So let's try this. We're going to look at an index of 3, negative 15, z squared to the 3rd power. Okay, and this is an example from our practice in Sabbath. So what would we do here? Well, I'm going to take this as my radicand. Okay, so that's going to be my base. I get negative 15z to the 2nd power to the 3 over 3 power. Well, and anything divided by itself is 1, so that's actually going to simplify my problem down to just, okay, negative 15z squared. So without having to expand everything out and deal with those other exponents, by using the radical to exponential form, I was able to get rid of that radical sign and actually simplify it down a lot easier than I thought it would be. Okay, let's keep practicing. Alright, here we go. Let's look at this next problem here. I'm just going through our text and trying to find the ones that are most challenging here. Alright, so what if it's asking us to find all of the 4th roots? Let's say of 16. Okay? We still have to use our factor tree and expand it out. So it'd be 2 times 8, 2 times 4, 2 times 2. So it'd be 2 times 2 times 2 times 2. Okay. And again, we're looking for groups of 4. So 4 2's get to leave, or 2 to the 4th power is 16. I have one group of 2, so 1 2 gets to leave. Okay, and then we have to think about, okay, well, are they all positive? Or could they have all been positive? Or could they have all been negative? Which one would work here? And what will help you is if your index is even, it could be plus or minus. Because if you have an even amount of negatives, you still get a positive. So here I can say it could be plus or minus negative 2. Okay? If they're odd, it could be positive or negative because negative 2 times negative 2 times negative 2 is negative 8. Negative 2 times negative 2 times negative 2 times negative 2 could be positive 16. It's going to give us a positive. So just keep in mind when we're multiplying, we have even numbers of negatives, they're going to become positive. If we have an odd amount, it could be a negative. Okay. So let's try this. What if we're asking for all the 3rd roots of negative 8. Okay, so I'm going to go ahead and factor it. 2 times 4, 2 times 2, but we're wanting third roots. Okay, so I know it's 2 times 2 times 2. We have to ask ourselves, would 3 positives give me a negative 8? No, because positive times a positive times a positive is always a positive. So that tells me I know for sure that these cannot be positive. They would have to be a negative 2 to give me a negative 8. Okay, because a negative times a negative times a negative is a negative times a negative is a positive times a negative is a negative. So I am going to make sense of this here, saying, okay, pause before I box in my answer. Is that going to be only a positive 2? Could it be a positive or a negative 2, or only a negative? Okay. So let's try a couple more here. Okay, so what if I've been asked to find the 5th root of negative 32? Okay, I'm going to go ahead and factor it. I'm going to use 4 and 8, 2 and 4, 2 and 2, 2 times 2, circle all my primes. So I've got my prime factorization now. Three, 4, 5, 1, 2, 3, 4, 5. 5th root, and I want to ask myself, okay, could it be, should they all be positives? Well, if they're positives, they're not going to give me a negative 32. So if they're negative, it'd be a negative times a negative is a positive, negative, positive, negative. So that tells me it should be a negative 2 to give me a negative 32. Okay? Or we can use our exponential form to help us with that. So if this is confusing you with the symbols, let's now try it with our exponential form. Okay, so you would still factor. Okay, so the 4 times 8, that's not going to change. And I'm just going to rewrite it and say, okay, negative 32, the 5th root of negative 32 is the same as negative 32. Oh my goodness. Okay, to the invisible 1 over 5 power, which then I can write it as negative 32 is the same as negative 2 to the 5th power raised to the 1/5 power. If I multiply these, our power to a power rule tells us to multiply our exponents. When I multiply, I get 5 over 1 times 1 over 5, which is 5 over 5, which is 1. So I then get negative 2 to the 1st power, which is negative 2. So I'm going to take it out of radical form, put it in exponential form, still use my prime factorization to get them to my power to a power, and then I simplify. Okay, let's try it again. And I'm going to do just the exponent form on this one. So here it is. We have the square root of 25. I know it's square root because there's not an index shown, so it's an invisible 2. I'm going to go ahead and fill in my exponent of 1. So again, I'm going to write it as exponential form. And that would become 25 to the 1 over 2 power. Okay, 25 is 5 times 5. Which would be 5 to the 1st power raised to the 1/2 power. second. There's 2. Silly. There's 2. So 5 to the second power raised to the 1/2 power. Multiply that across, we get 5 to the 2 over 2, which is just 5 to the first power. Positive 5. Now, could it be negative? A negative times a negative would still give me a positive, so it'd be plus or minus. Again, remember, if it's even, you're going to use plus or minus. Okay, let me do one more with variable terms, and then we can move to our next type of problem that we've seen here. Okay, so again, if there is not an index, it's an invisible 2. So how I can write this is 25 to the, here we go, 25x squared to the, I'm going to put all of this in one, to the 1 over 2 power break this apart. It would be 5 times 5, so that would be 5 to the second power, x to the second power, all raised to the 1/2 power, which would be, again, a power to a power rule. They're next to each other with that parenthesis, so we'll multiply it. And I get 5 to the 2 over 2, which is 1, x to the 2 over 2, which is 1. And I'm getting that because 2 over 1 times 1 over 2. 2 times 1/2 is 2 over 2, which is 1. Okay. So, it would be, our solution would be the absolute value of 5x, because it would always be positive. Okay, let's try a couple more. What if I am looking for the 4th root of 4? Okay, so again, I'll put my little invisible 1 there. Well, it would become 4 to the 1/4 power. I'm going to go ahead and factor my 4, which would be 2 to the second power raised to the 1/4 power. Now I'm going to multiply 2 times 1/4, multiply across, reduce, and I get 1/2 as now as my exponent, 2 to the 1/2 power. And what if they ask us to write that back in radical form, since that's how we started, but we want to simplify that. So we'd take it back to exponential form, and then I can take it back to radical form. So it'd be 2 to the 1 over 2, right? So it would end up being square root 2, and you would really just see it like this. You're not going to see the invisible 1 exponent, you're not going to see the invisible 2 as your index. Okay, just a couple more examples. I want to give you as many as I can without making my video run too long here. So again, go ahead and take it to exponential form. So it'd be x to the 2 over 4 power. Okay, x did not have, I can't expand it, it's not repeated here. So that would just become, I could reduce it by 2, x to the 1/2 power, which would then be, again, x to the first power with an index of 2. And again, both of those are invisible, so it'd just be square root x. Okay. So x to the 4th power, the 12th root of x to the 4th power. Again, x to the 4 over 12, that reduces by 4, and we get 1 over 3, which would become x to the first power with an index of 3. And again, the 1 would be invisible, so it would just be square root 3. Okay, let's look at some crazy ones. What if I wanted to find all the cubes of negative 729? what would we do here? Well, let's write this in our exponential form, the invisible 1 over 3. I will go ahead and use my factor tree, factor this out. It would be 9 and 81. 9 times 9. And again, I'm going to stop and think, okay, should it be negative or positive here? Well, I need it to be a negative, and I have 9 to the third power. So a negative times a negative times a negative is a negative. So I'm going to say negative 9 to the third power raised to the 1/3 power. So what I'm saying is this negative 729 becomes negative 9 to the third power in exponential form. Okay. Now, a power to a power rule means I would multiply, so I'd get negative 9 over 3 to the third power, which is negative 9 to the first power. So therefore, all cubes of negative 729 are negative 9. Let me show you one where we have a positive. Okay. What if it wants to know all the fourth roots of 6,561? Okay, so fourth root of 6,561. Again, I'm going to go ahead and put that in exponential form. Remember the invisible 1 over 4. So 1 over 4. Use my factor tree. Use 81 times 81, which is 9 times 9, 9 times 9. Which I can stop there because that's my fourth power right there. So I didn't have to break it all the way down. I can just say, okay, 9 to the fourth power raised to the 1/4. And since it's positive, then they could all be positive. But they could also be negative, right? Because a positive times a positive is a positive. If I have an even amount of negatives, or that's also going to give me positive. So it could be a positive plus or minus 9. Okay, so plus or minus 9. 4 to the 1/4 power is 1. Well, I'll go ahead and put it 4 over 4, which is 1. So my answer is positive or negative 9. So just be mindful of your negatives. Take your time there because they can be very sneaky. But remember, if it's an even amount on our index, then it's going to be plus or minus because an even amount of negatives is a positive. Okay? And if it's negative, it could be negative or positive. Just take it, slowly. If it's negative here, it's going to be negative in your answer. Okay? If it's positive here, it could be a positive. It will be a positive. So if this is negative, this will be negative if you have an odd amount. Okay?